Could a heavy rainstorm be deadlier than an eruption? Could the quiet slopes of a sleeping volcano suddenly send a concrete-like wall of mud tearing through a valley without a single plume of ash rising from the summit? In late December, a string of Pacific storms tested that possibility on the Cascades of Northern California. The danger was not molten rock, but a simpler, older recipe: rain, snowmelt, and loose volcanic debris. This is a technical, on-the-ground look at how Lassen Peak and Mount Shasta can produce deadly lahars without erupting, why their geologies make them especially vulnerable, and why a sequence of atmospheric rivers in December heightened the risk. A lahar is a slurry of water and volcanic debris that behaves like a river of wet concrete. Its basic ingredients are water, which supplies the fluidity, and a stockpile of volcanic sediment, ash, lapilli, blocky debris, and weathered volcanic rock, which supplies the mass. The physical behavior of a lahar depends on the grain sizes, the water content, and the slope and confinement of the channel it occupies. Coarse, boulder-rich flows move like viscous landslides, punching through bridges and burying channels in thick deposits. Fine, ash-rich lahars can travel farther as hyper-concentrated flows that maintain high mobility even at low gradients. The mechanics are straightforward, but the stakes are high. A lahar's density is often comparable to wet concrete. Its velocity can be tens of meters per second, and its capacity to entrain additional sediment means a small initial failure can grow into a long-run-out, high-impact event. Mount Shasta and Lassen Peak share a common set of features that predispose them to rainfall-triggered lahars. Both construct steep edifices from alternating layers of lava, tephra, and weakly consolidated pyroclastic deposits. Both have histories of explosive activity that produced large volumes of fragmented material spread across their flanks. Both retain significant snow and ice at high elevations that can be rapidly mobilized by warm rain. And both sit above river systems that can channel any mobilized sediment many kilometers from the summit. These are the geometric and material conditions that turn a storm into a lahar generator. Lassen Peak is a dome built near the center of a broader volcanic complex. It rises to about 10,457 feet, about 3,187 meters, above sea level, and is the most recent expression of a volcanic field that has produced hundreds of eruptive episodes over hundreds of thousands of years. Its 20th century eruption sequence, which culminated in May of 1915, is the best modern example of how an eruption and snowmelt combine to make catastrophic flows. In that event, a growing summit dome became unstable, producing a dome collapse and a high explosive ash column. Heat from the collapse and from pyroclastic currents melted the seasonal snowpack on the volcano's slopes. Meltwater poured into hot ash and fragmented rock, and the mixture surged downhill as lahars that reached tens of kilometers from the vent and scoured drainages far beyond the immediate summit area. The lesson from Lassen is clear. Ash and fragmented deposits left by eruptions do not need fresh eruptive heat to become mobile. The deposits themselves are mechanically weak and often hydrothermally altered. Chemistry and hot fluids during and after eruptions alter glassy ash and young volcanic rocks into clays and friable minerals. These alteration products reduce internal cohesion and increase erodibility. When rain or meltwater infiltrates them, the deposits can rapidly lose strength. A slope that appears stable when dry can fail catastrophically once the pore water pressure rises enough to reduce effective stress. That mechanical failure is the trigger. Once material starts moving, the falling mass can entrain more sediment and water, evolving into a full-blown lahar. On Lassen, much of the critical material lies in valleys and fans that record the volcano's recent explosive past. Layers of ash, pumice and blocky pyroclastics sit in stream channels and on the hill slopes above those channels. These layers are both the source material and the path. When heavy precipitation or abrupt snowmelt delivers water, it concentrates in channels and shallow subsurface flow paths. The combination of saturated sediment and steep channel gradients promotes rapid mobilization. Because the deposits include a wide range of grain sizes, from silt-sized ash to meter-scale blocks, the resulting flows can vary from hyper-concentrated mud to boulder-laden debris flows, each with different run-out behavior but all potentially destructive. Mount Shasta is larger and higher than Lassen. It towers to roughly 14,163 feet, about 4,317 meters. It was built atop the remnant remains of an earlier, catastrophically collapsed volcano. That prehistoric collapse moved hundreds of square kilometers of material downslope and left a landscape predisposed to later slope failures. Over the Holocene, Shasta rebuilt itself with numerous flank vents and tephra blankets. Its eruptive history includes explosive events that generated abundant fragmented material on its flanks and valley floors. Because Shasta's summit and upper flanks are high and cold, glaciers and perennial snowfields persist. They act as stored water when warmed. The important point for Shasta is twofold. First, its flanks contain widespread and deeply entrenched deposits of loose pyroclastic material, sometimes capped by more resistant lavas, but often exposed to erosive processes. Second, many of the steep drainages that radiate from the summit terminate in populated valleys and transport corridors. Historically, Shasta has produced numerous debris flows and lahars during both eruptive and non-eruptive periods. Geologic mapping shows lahar deposits reaching tens of kilometers from the summit, and many modern channels follow routes defined by those ancient flows. When an extreme precipitation event delivers water rapidly into those channels, the combination of steep slope, loose sediment, and concentrated flow paths becomes the perfect setting for initiation and propagation of lahars. Why does heavy rain do the job so effectively? The process begins with infiltration and saturation. Volcanic ash and tephra are often composed of angular glassy fragments that pack poorly and have high porosity. Dry ash can be deceptively stable. Saturated ash, in contrast, can lose frictional strength rapidly. Two mechanical effects are important. First, increase in pore water pressure reduces the effective stress that binds grains together, lowering shear strength and making slopes more susceptible to landsliding. Second, once water flows over or through a deposit, it can physically detach particles and transport them down slope, a simple entrainment process that grows exponentially as more sediment is mobilized. In channels, the turbulence of flowing water suspends fine ash, increasing the flow's density and giving it the erosive power to scavenge coarser material. A small sheet failure or bank collapse can thus draw in additional sediment and water, evolving into a fully developed lahar. Snowmelt acts like a multiplier in this system. Warm rain on snow rapidly increases runoff because the rain contributes to both runoff directly and to accelerated melting of the snowpack. The presence of snow amplifies the volume of water delivered during a storm, and it does so quickly. In the context of high-elevation volcanoes, where snowfields and glaciers store winter precipitation, A single warm atmospheric river can produce runoff volumes equivalent to multiple days of ordinary rain. That sudden influx overwhelms channel capacities and increases the likelihood of bank collapse and sediment mobilization. On steep volcanic flanks, a surge of meltwater can saturate deposits from above, while simultaneously scouring channels from below, creating the bilinear condition for Lahar initiation, a saturated source area and an efficient transport pathway. Hydrothermal alteration is another key factor that often goes unnoticed by the public. Volcanic systems commonly host circulating hot fluids that alter primary minerals. Ash and volcanic glass recrystallize to clays and weak secondary phases. Lavas develop fractures and weather into friable blocks. Altered rock is mechanically weaker and more water-sensitive than fresh, unaltered rock. On Lassen, hydrothermal alteration in areas around the summit and within older dome complexes has produced zones of fine, cohesive but weak material that readily slumps when saturated. On Shasta, fumarolic activity and thermal springs indicate persistent heat flux in places where old hydrothermal systems have altered deposits. The sheer strength of those deposits can be greatly reduced. In essence, hydrothermally altered volcanic material is primed to fail when wetted. Another mechanism that deserves attention is the role of surface armoring and subsequent failure. Over time, stream channels often develop a surface layer of coarser material that protects the finer ash underneath. During normal flow conditions, that armor layer reduces erosion. However, extreme flows can remove or breach the armor, exposing the underlying fine ash and enabling rapid entrainment. Once the fine material is available, the flow density and erosive power increase, allowing the Lahar to entrain even larger clasts and to sustain long travel distances. This is why small breaches early in a storm can be disproportionately important for the eventual size of a Lahar. The December storm sequence provides a concrete meteorological trigger to these processes. In mid to late December, a series of atmospheric rivers tracked into the west coast. The first of these storms brought warm, moisture-rich air into northern California over roughly 2 days, delivering heavy rainfall across the coastal and mountain ranges. The second system followed quickly, extending the period of high moisture and keeping soils and snowpack in a saturated state. The third storm in the sequence was the strongest and lasted through the Christmas period, producing persistent heavy rain and elevating freezing levels well above typical winter heights. The practical consequence for Lassen and Shasta was that much of the precipitation fell as rain across elevation bands that would otherwise have received snow. Where snow existed, it experienced rapid melt. The combined effect was prolonged saturation of hill slopes, channels operating at or above bankfull, and repeated hydraulic forcing on valley walls and sediment deposits. From a hazard perspective, this combination, persistent rains, elevated freezing levels, and a sequence of storms without long recovery time, is exactly the condition that exacerbates Lahar risk. The first storm soaks the ash and weak rock. The second storm prevents drying and continues to add water. The third storm may tip marginally stable slopes into failure. Importantly, the return interval for such atmospheric river sequences can be short. When storms come in quick succession, there is little time for the landscape to drain or consolidate. Channels that might survive a single storm can be primed by the second and third events to produce bank collapses and full channel scouring. Why does the U.S. monitoring community regard Lassen Peak and Mount Shasta as high-threat volcanoes even when they are not erupting? The answer lies in a combination of persistently available source material, geomorphic setting, and exposure. Both volcanoes have abundant fragmented deposits on steep slopes. Both have drainage systems that lead into populated valleys. Both have histories showing that debris flows and lahars can reach far beyond the summit. Threat classification is not solely a metric of eruptive frequency. It is a measure of the potential for hazardous processes to impact people and infrastructure. In the case of these two volcanoes, the legacy of past eruptions, the loose ash, the altered rocks, the entrenched Lahar channels creates a significant non-eruptive hazard. Add to that a modern human footprint of roads, bridges and towns situated on depositional fans, and the consequences of a lahar become clear. Monitoring for lahars is challenging. Eruptive signals like increased seismicity, gas emissions or ground deformation can give warning when an eruption is imminent. Lahars triggered solely by rain or melt are governed primarily by hydrological variables: rainfall intensity, snow melt rate, antecedent moisture, and slope stability thresholds. While rain gauges, radar, and hydrologic models can provide alerts for flood and debris flow potential, the exact timing and location of a lahar remain hard to predict at fine scales. This means that meteorological forecasts, particularly of intense or prolonged atmospheric rivers, become a critical component of lahar risk management in volcanic regions. The physics of flow transformation also explains why lahars can be disproportionately destructive relative to their initial triggers. A slope failure or channel bank collapse may mobilize a moderate volume of material, but once an erosive flow forms, it can entrain additional sediment downstream, increasing both volume and destructive power. The flow's stratigraphy may show a progression from dilute, ash-rich surge to denser clast-rich debris as the flow matures. This maturation process allows lahars to persist over long distances. They do not simply stop when the initial trigger ends. Consequently, areas many kilometers from a volcano can be inundated even when the triggering rainfall had ceased several hours earlier upstream. Looking at probable pathways, the primary concern on these two volcanoes is the networks of steep, confined channels that feed major river systems. On Shasta, upper tributaries that join the Sacramento and McCloud river systems act as conveyor belts, narrow headwater channels into which a lahar can collapse banks and entrain valley fills, then expand into broader, high-energy flows as they move downslope and pick up more water and sediment. On Lassen, smaller streams draining into basin floors and reservoirs are equally vulnerable. Lahars can deposit thick, cohesive layers that alter drainage patterns and create long-lasting hazards, such as dam channels that may later fail, but also long-term recovery challenges. So, what then separates a dangerous scenario from a manageable one? It is a combination of timing, intensity, and location. A short, intense burst of rain that coincides with already saturated slopes or with rapid snowmelt in a key drainage is far more dangerous than the same amount of rain distributed over a longer period. A breach in a channel's coarse armoured layer at a strategic upstream point can trigger downstream evolution into a major lahar. And when those channels lead into populated lowlands or infrastructure corridors, societal risk is magnified. The December atmospheric river sequence illustrates all these elements. Warm, moisture-rich air causing rain at elevations that would normally see snow, repeated storms that maintain saturation, and known supplies of loose volcanic material on steep slopes that needed only a trigger to fail. That does not mean a lahar will inevitably occur after every such sequence. local variables, the thickness and distribution of unconsolidated deposits, the location of armoured channel beds, the presence or absence of prior bank failures govern the actual initiation. But the climatological conditions increase the statistical likelihood of a lahar on flanks where material and geometry already predispose the landscape to failure. Finally, it is worth underscoring the human dimension without departing from geology. Modern communities often sit in valleys shaped by past lahars and therefore appear deceptively flat and habitable. Those same fans and floodplains are the exact places where future lahars will want to deposit their loads. Planning and emergency response must account for non-eruptive volcanic hazards as well as eruptive ones. Monitoring agencies use rainfall thresholds combined with knowledge of volcanic sediment inventories and channel geometries to issue warnings. But the geological reality is immutable. Where a volcano has made ejecta and left it on steep slopes, water will sooner or later find a way to move it. In the end, an eruption is dramatic and visible, but the quieter combinations of rain, snowmelt and ash can produce outcomes that are equally deadly. Lassen Peak and Mount Shasta are textbook examples of why volcanoes remain hazards even in repose. Their histories have written a catalogue of debris flows, altered materials and long lahar runouts into the landscape. When a string of atmospheric rivers delivers warm, abundant precipitation to those slopes, the odds shift toward activation of that catalogue. The risk is not theoretical, it is a consequence of the physical processes that govern sediment stability and fluid flow on volcanic terrains. Understanding those processes is the first step toward effective risk reduction. And a reminder that in volcanology, silence at the summit is no guarantee of safety downstream. If you found this breakdown valuable, don't forget to like the video, share it with fellow science enthusiasts, and subscribe for more deep dives into the forces shaping our planet. Your support really matters, so tap that hype icon and help this video reach a wider audience who wants real science, not just headlines.